that resulted in everything moving apart from everything else? And this is a question that was on the table for many decades. And it was really the work of the more modern collection of cosmologists, people like Alan Guth, Paul Starner, and Andre Linde, who really took this up. Now when you look at this picture right here, you immediately see that modern cosmologists, compared to their earlier counterparts, are really happy. You know, and part of the reason they're so happy is because so much progress has been made. So these folks came up with what's known as the inflationary theory of cosmology, where they basically found, again, in Einstein's mathematics properly interpreted, they found that Einstein's version of gravity allows for a repulsive gravitational push, as opposed to the usual that we're familiar with. We're all used to gravity that causes things to come together. They found that in exotic circumstances that they believed, they proposed, prevailed in the early universe. They said that there was an energy field that filled space, and the math showed that this energy field would not give rise to a gravitational pull, but rather a gravitational push. And this energy field is called the inflaton field. The names, of course, do not matter, but the idea is that that is what drove the outward swelling. And the beauty, again, of this is not just words, it's not just animation, it's not just pictures, it's mathematics. And the mathematics makes predictions. And this inflationary theory makes a prediction of a very specific sort. It says if you could measure the temperature of space, temperature in one location, another location, another location, the math shows in this theory that the temperature should vary slightly, 1 part in 100,000, tiny temperature variations throughout space. And that's represented in this little picture here by the different speckled colors. Blue is one temperature, red is another, orange is another. So as you see, there's tiny temperature variations across the night sky. And the pattern of this temperature variations is picked out by the mathematics. And remarkably, we now have, over the course of, let's say, almost 30 years, made ever more refined measurements of the temperature of space, sending up satellites, sometimes in balloons, sometimes actually above the atmosphere, that have measured the temperature of space. And I'm now going to show you the data. And I'm going to show you the data in a way that you don't need to fully understand exactly what I'm plotting. It will just be the agreement between theory and observation that matters. But let me just tell you. So I'm going to plot how the temperature varies as a function of the angle across the sky. That's what I'm going to plot. And then I'll show you the data of the measurements. And we'll see whether or not they agree. So here is the mathematics of how the temperature should vary across the sky. And here are the data points, and I'll just be quiet. Wow, right? I mean, to my mind, this is as beautiful as the Mona Lisa, right? It's just a spectacular achievement that we little puny beings crawling around the surface of this planet are able to come up with mathematical equations that predict how the temperature should vary. We measure that temperature by capturing photons from space that have been traveling for nearly 14 billion years. We capture these photons, we measure them, and their properties agree with the mathematical prediction to this spectacular precision. And that's what gives us confidence that at least we're going in the right direction in our pictures of the universe. And this then takes me to my final point, which is this. When we look at the mathematics, let me go back to the math now, using this as my confidence for going back and taking the math seriously. Using the mathematics, here's the interesting feature. This fuel, this inflaton field that drives the repulsive gravity, the math shows that it is virtually impossible to ever fully use that fuel up. Some of that fuel powers our Big Bang, but some is left over. What does the leftover fuel do? It powers its own Big Bang, a second Big Bang, but then there's also some fuel left over. What does it do? It powers a third Big Bang, a fourth Big Bang, and so forth, each giving rise to its own distinct, separate universe. So the picture of that then would be something like this. Our Big Bang, fuel left over, other Big Bang, other Big Bang, other Big Bang, and so forth. So each of these spheres now is not a planet or a galaxy. These are meant to be distinct universes, with our universe just being one in this big collection. So then the idea would be, if we pull out from planet Earth, and we pull out past the other planets, and we say pull out of the Milky Way galaxy, and we keep on going, and in some metaphorical sense, we pull outside our universe. The idea would be, we are one among many universes floating in a much grander, much richer, much more unexpected reality. Now, is this idea right? We don't know. And there are possible ways that we might actually test for this, that I'm happy to address if anybody wants to ask a question about it. But the larger point is how remarkable it is to go from Isaac Newton's version of reality is pretty much what you see is what you get. And he adds a mathematical overlay to that, allowing us to make predictions. You know, if you drop a teacup, how's it going to fall? It's all pretty much what you'd expect based on your experience. And then we march through the centuries, and little by little, our picture of reality, our picture of space and time radically changes. Einstein put space and time together, realized that space and time warp and curve to yield gravity. Space and time can ripple. Space and time can create these wells that we call black holes. Space and time can expand. And now we learn that space and time that we are familiar with might be a little tiny nugget in a much grander reality populated by other universes. And to my mind, you know, if we can at some point, maybe it's tomorrow, maybe it's 1,000 years from now or 10,000 years from now, if we can actually get experimental data establishing this picture, in some sense, that will be the most complete version of the Copernican revolution, right? We used to think that we were in the center, right? Everything revolved around us. And then, no, the sun is in the center, and we go around the sun, but at least the sun is the center, right? And then we learn, no, actually, the sun is one of 100 billion stars in the Milky Way galaxy. But the thought was at least the Milky Way galaxy is all. No. There are 100 billion other galaxies out there. We're just in an ordinary galaxy. In fact, we're just a little suburb of a particular arm of this galaxy. If now we learn that the entire universe is itself just one of a grand collection of universes, it will be, in some sense, the grandest cosmic demotion. But at the same time, how wondrous that somehow this 3-pound gloppy gray structure inside of these bipedal beings who are scurrying around this rock, orbiting a nondescript star in the outskirts of a nondescript galaxy, can somehow figure this all out. To my mind, that is really what the story is about and what makes this all utterly spectacular. So, thank you very much.